Okay.
Which I probably turned into a candle.
Okay, let me wait maybe one more minute before we get started, so folks can slowly join. You're our first non-local colloquium speaker of the quarter. So I think it's exciting for everybody.
Awesome.
I
can see we are getting good attendance. That's great.
We had lunch with the grad students too, right?
Marcelle,
Yes.
Yeah.
That's awesome. Yeah, that's one of our in-person traditions. So I'm glad they're continuing.
Yeah, we had a very lively chat. It was very good.
That's great. What was I guess did they typically ask what's the most expensive thing you ever broke? Did you get that question?
I was about to ask her that. I'm glad someone else did.
Yeah, I evaded that question. Don't want to set a bad example, but yeah. But talked about totaling the experiment shared car on a trip to Chile when we were installing the camera. I guess that counts.
I think that counts.
Yeah. Okay, so I'm gonna go ahead and get started. Hopefully people will slowly trickle in. I'm doing both admitting and introducing, so some folks will have to wait in the waiting room for a little bit. So we're really happy today to have Marcelle Soares-Santos give our colloquium. Like I was mentioning, she's the first non-local colloquium of the quarter, so it's always exciting to have somebody from outside of Eugene come visit, even if it's virtually. So a little background about Marcelle. She is Brazilian and received her PhD from the University of Sao Paulo before moving to Fermilab outside of Chicago, Illinois, to do a postdoc, and then was later was a scientist at Fermilab. After that, she moved to Brandeis as an assistant professor, and more recently, I guess this year, moved to the University of Michigan in Ann Arbor to start her group there. So Marcelle's research focus is on understanding the accelerated expansion of the universe and studying dark energy. And she's a member of the Dark Energy Survey and has really been instrumental in spearheading this program within DES to look for optical transients that are associated with the LIGO Virgo events. And this is like heralding this era of multi-messenger cosmology. Those of you who were very excited about the neutron star merger in 2017 might recognize Marcelle, as she was the invited speaker for the NSF press conference. So she was the one who made the announcement about the discovery. So we're really honored to have her tell us about this really exciting program about multi-messenger cosmology. And Marcelle is happy to have you all ask questions during the talk. So if you have a question, I'll ask that you use the raise hand feature in Zoom. So that you can find in, if you go to the participants panel, there'll be a raise hand button. So raise your hand and I'll call on you. Okay. Otherwise, I'd ask that you please mute your mic. And with that, go ahead and get started.
All right. Thank you. Hello, everyone. It's a pleasure for me to be here and talk about this work, which for me is fascinating. And I'm really excited to see so many of you connected and to hear about this work. So I'd like to start showing this image, which is the image I'm most proud of. This is the discovery image that we made of GW 170817, the neutron star merger that was the first and so far the only observation that we've made of the optical counterpart of a gravitational wave event. So what you're seeing there highlighted here by the crosshairs is this source is the location where the merger occurred. And this image here on this side was taken, it's a combination of images taken on the night of and the following night post-merger. And here on the side for comparison is an image of the same region of the sky taken in similar conditions 2 weeks later. And as you can see, the source is no longer there. I like to start showing this other than being a pretty picture for your enjoyment. I like to start showing by showing this image because it also illustrates the challenges of this type of research. And for the non-astronomers in the room, you will see clearly that the source here at its peak brightness, it was, let's say, let's not necessarily talk about fluxes and magnitude units here, but if you just compare with other bright sources in the same field, it is bright, although not as bright as the entire galaxy that is hosting this event, right? And 2 weeks later, it's just gone. So the first challenge there is how do I identify a little dot in the sky in a field that has tons of other objects? And how do I do that promptly because the source will fade away? Another thing that you will notice here is the fact that in this case, the source is a little bit offset with respect to the center of the galaxy. As you can imagine, it would be a lot more challenging if the alignment would be different and it would be right on top of each other. So this type of observational challenges are the type of thing that I have to think of when designing the program to observationally attempt to do a discovery like this. And what I'm going to talk about today is a little bit about the journey that we went from designing that system and finally achieving this, and what we've done since then. This event was observed in 2017, and since then we've been very active in a program that pursued a number of other events and is trying to get to cosmology. And those of you who know me know that my passion in terms of science is cosmology, and specifically trying to figure out what dark energy is, what's causing the accelerated expansion of the universe. And so it's with this motivation that I pursue this science, although I'm very aware that there are a number of other investigations that are enabled by this. For example, astrophysics, nuclear physics, and so on. So let's really dive.
Sorry, there's no way Tian can see 73 raised hands, so I just like question from a non-astronomer on your first slide. How do you know that bright dot that disappears is physically associated with that galaxy in the first place?
Oh, that is a very good question. Thank you for asking this. So how do we know that this is not simply projection, right? Yes. Or something like that, exactly. So there are a number of things here. One of them is that we know what is the distance to this galaxy, and we know that this offset here corresponds to tens of kiloparsec. So this size is a typical size. It would be reasonable separation. We also have the spectrum of these objects, so we can tell that they are at the same redshift. So in the projection in the sky, right, they're next to each other. But in addition to that, another thing that we can use to tell here is, statistically speaking, you can ask the question, well, how likely it is that this object will be associated or not to this source, and that's another way that you can do that as well. In this case here, because the statistical method you usually do when you have many objects, right? That could be the host. Say you are in a crowded region with tons of galaxies. But here, because it's very isolated, it was quote unquote easy because we had the spectrum of them, so we can tell that the distance to this galaxy, also we have the distance from the gravitational waves, right? Is the same distance to this other galaxy. So it's not a projection. They are actually in the same plane in the sky. Thank you for the question. That's okay.
Thank you. Thank you.
So onwards
Excuse
to
me,
the
I just want to
cosmology
comment that.
motivation.
So
Yeah.
the gravity wave detection tells you how far the gravitational wave source is, which you're assuming is the source that disappears in these two visual images. But the gravitational waves don't tell you how far away the galaxy is. That you need to get from the spectrum and the redshift and so on.
Exactly. That's what I meant.
Okay.
Yeah, we have the
Just want to be clear on that.
Uh-huh.
Okay. Thanks.
All right. So on the cosmology motivation, this plot here is a few years old, but I like this one in particular for a reason that will become clear very shortly. So what you're looking at here on the x-axis is h0, the rate of expansion of the universe today. And the points here are different measurements from different observables. The ones to pay attention to are the ones in red here. They are all collection of measurements using type 1a supernova as standard candles. And the black points here correspond to measurements made with a cosmic microwave background, which is a measurement based in the early universe, data from the early universe. And as you can see, in particular, if you look at the most recent result as of the time of this plot, in comparison to the most recent result from the cosmic microwave background, they are not in agreement. At the time of this plot, the disagreement between these two was at about 4 sigma. And basically this trend has been growing over time. The more precise the measurements get, the more discrepant they are. Now, of course, that you could say that there is some systematic uncertainty, and both these measurements are very tricky to make. So there could be some systematic uncertainty that is unaccounted for that could make these results agree with each other. But if not, then it must be physics that is happening. And it could be that the physics that is leading to this is related to dark energy. And these arrows up here, they illustrate by how much the Planck result would move towards the supernova results. Again, this is from a paper by a very well-known famous supernova person. That's why the arrows go this way. Otherwise it would go the other way, right? But it's showing by changing the parameters of dark energy. And for the non-cosmology people in the room, this W0 is the value of the equation of state parameter of dark energy today. And we think that if dark energy is a cosmological constant, this number is -1. So if I change this number by 10%, this is the amount of shift that we get on the Planck result. If in addition, I allow the value of this W parameter to be not a constant, but varying with time, and the first derivative of this is given by this parameter WA. If I change this parameter, this is the amount of shift that I get. If I allow the universe to have a non-zero curvature, I get also little shift. And in particular, if I, instead of dark energy, if I change the number of neutrinos existing in the early universe, changes an effective value. So this one is the one that my colleagues from the neutrino field really like, because sterile neutrinos, for example, are a candidate for that. This is the amount of shift that you can get. All of these shifts here are allowed by the uncertainties in the current data sets. So it is really exciting to disentangle this and figure out or rule out the possibility of being systematic uncertainties, because if that's the case, that is a smoking gun of new physics, and that's really exciting for us. So this is why, in case you were wondering, and this is the reason why this H0 parameter is such a hot topic these days, because it's really likely to be, again, it could be systematic uncertainties, right? But it is likely to be the key to understanding what dark energy is. And so that's why we are so excited about that. Now, how do we do this, right? There are different ways of doing it. One of them is to find other observables that can be used for that. Another way is to dig in and try to make your measurements in your favorite observable, either here or here, better, with new ways to handle systematic uncertainties, et cetera, and the community is very active in all those fronts. Now, wouldn't it be great if we could add a new point into this plot that would be from an independent observable, some quantity that depends on different sources of systematics that we can control and et cetera, that could arbitrate between these two measurements. This would be fantastic to be able to do that, and gravitational waves might be a way to do this. Now, before I go into adding something new to here, let me talk about the program that we do with the Dark Energy Survey. If you're not familiar with the DES, DES is a survey that actually has just completed data taking in last year. And so now we are analyzing the full data set and producing papers and so on. It's a really exciting phase of this experiment. The survey covered 5,000 square degrees, or 1/8 of the entire sky, in multiple filters in the optical bands. It also covered 30 square degree areas repeatedly looking for supernova, so that we can put our own supernova dot in this plot. As of 2014, we added a program that we call DESGW, which seeks optical counterparts of gravitational wave events. A spin-off of that is that some events from the Ice Cube experiment in the South Pole, some neutrino events, we think that they could come from astrophysical sources that we could detect as well. So we use the same code to look for some neutrino events as well. To do this, all this rich, observational program, the Dark Energy Survey uses a camera that we call DECam, the Dark Energy camera.
Excuse
Go
me,
ahead,
Marcelle,
yeah.
So I understand what a gravity wave event is. What's a neutrino event?
Oh, this is a neutrino detected, for example, by the Ice Cube experiment that is at South Pole. So when the neutrino is...
So when you say an ice cube event, you mean when the ice cube suddenly detects a lot more neutrinos than it usually does? It's a burst of neutrinos at the ice cube.
Yes, a burst of events that they reconstruct and say, oh, these are neutrinos coming from that region in the sky.
I see.
Exactly.
Okay. Mm-hmm.
Yeah.
Okay.
And
do we usually
models,
imagine those as coming from supernovas, or?
Yeah, so
is it a mystery
one
what
of
they
the
come
models, it is a mystery where they come from, and there are models that say that certain supernova can generate these events, can accelerate them. And so we look for them. We haven't found anything, otherwise we would have made a big splash out of it. But, but yeah.
Okay.
Currently, the most likely thing that people consider to be the sources are AGMs, right? And that would be a different type of setup. Okay, so the camera, as I was saying, is called the Dark Energy Camera, or DECam for short. It's a 3 square degree field of view camera with 570 megapixel, the one that we installed in Chile back in 2012. And the great thing about this is a wide field of view camera on a large telescope. And the combination of these two factors is important because, as you know, we are looking for sources that are very faint, and we have to cover a large area of the sky because, as you will see later, the gravitational wave events are not very well localized, so a wide field of view is very important. Now, the DES is up and running for several years already, since 2012, when the camera was installed on the telescope. We have produced some results, some cosmology results already, and more are coming. This plot here is from a paper from 2017, and it shows here two parameters: omega m, the total amount of matter in the universe, and S8, which is the amount of clustering of matter in the universe. Those parameters are two parameters that we are very sensitive to. And dark energy affects these parameters here too. So what I want to call your attention here is that our result from DES is the blue blob here, and the result from Planck in the same parameter space is here. So you see that the contours still overlap. This is 1 sigma, 2 sigma, but they don't overlap so well, you know. So again, I wouldn't call this a tension, and in particular, I wouldn't call it as a strong a tension as the one you see in H naught. But I'd like to show this plot, and we have several others. This is only one example of places where this type of tension between the CMB and other observables that we call local, meaning observables that are in the not in the early universe, but in the modern universe where galaxies, etc., exist. The tensions, they seem to be popping up in various places of the parameter space. And that is another way that, you know, this type of thing is intriguing and we want to pursue further, because it is very hard to imagine one particular source of systematics that would, you know, push all of these results to be in tension in the same way. It is likely that it's actually physics that's happening, so we want to explore it further. So let's go diving into how the gravitational waves can help us. This is a printout of one of the first papers that suggested using gravitational wave events as distance indicators to measure the Hubble constant. And of course, I don't expect you to read all of this, but I like to show this paper because I keep saying that when I grow up, I want to write papers like this, 3 pages, no figures, couple of equations only, and a hell of an impact. In this paper, the equations that are relevant are these two here. Equation 1 shows the amplitude for a binary system and using the standard quadrupole formula from Einstein's theory. The first equation shows the expected amplitude of the gravitational waves as a function there of the masses of the two components of the binary, and as a function of the distance, right? And equation 2 shows the rate of change in frequency, f dot over f, that gives us a time scale tau. And the key component here is the fact that masses, frequency, go into this, the masses in particular, they go into this formula with the same exponents as they go into this other formula here. So that means that if you measure in your detector the rate of change in frequency, you have an estimate of this combination of masses that you can plug in equation 1 and get the intrinsic amplitude of your waves, which means that you can compare that with the amplitude observed in the detector, and the ratio between the two gives you the distance. So this is in a very hand-wavy way telling you how these events can serve as distance indicators for cosmology. All you need to do is detect several of these and you have the distance. And then if you point your camera and find the optical counterpart, you can get the redshift and you can build a Hubble diagram, distance versus redshift, and boom, measure H naught that way. That's the idea. Simple in theory. In practice, it took several decades before we could get there. And even after you get to the point where the detection of gravitational waves happen, there is a challenge of finding the counterparts. And this plot illustrates, this was made by 2 of my collaborators, and it illustrates how challenging that is. What you're seeing here is for simulated events. On the left side is in the case where you have 2 detectors, the 2 LIGO detectors, and on the right side here, you see the impact of adding Virgo, a 3rd detector. On the y-axis, this is area in the sky in square degrees. Remember, the celestial sphere has 40,000 square degrees. This is substantial area. And even though it's an order of magnitude less than here in average. So here, cooking down these numbers into 50% and 90% confidence levels here, you get that you need to cover areas of about 60 square degrees to reach 90% confidence level in average to be able to detect something. Now, this is, for the non-astronomers in the room, this is challenging. It's not easy to cover. If you're looking for a faint source, it's not easy to cover all this area. But as I said, our camera has 3 square degrees field of view. So 60 square degrees is not that many pointings of our camera. We can do that. That challenge is not impossible. So how do we do this? In order to accomplish this program, what we did was partner up with LIGO. We were not the only team to do that. LIGO issued a broad call to the community, and everybody who had the resources signed up to receive the triggers. That means alerts that you receive saying an event happened in that region of the sky, go there and look. Our code would then make an observing plan that was tailored for our camera in the Blanco telescope. What you see here is the Blanco telescope in Chile. Once the observations happened, we would take the raw images and pipe them through our image processing pipeline and all the way to produce a list of candidates. We did, especially in the early days, we did a lot of the vetting of the list of candidates by hand. We have a team of very dedicated students and postdocs that worked tirelessly on this. And then we run a post-processing code that gets us some statistics, etc., until we are able to issue a public list of possible candidates. Here's an example of how long it takes to process those images. If you want to see details of how the sausage is made, the behind the scenes of the processing, the strategy, and so on, I highly recommend reading this paper where we summarized and made an overview of how this was done. Now, if you want to
Marcelle,
yes?
sorry. It sounds like to make this whole process work, you have to have this telescope at your disposal at a moment's notice. Is that the case?
Yes. Yes.
I was assuming you guys had to beg for time and you got a certain slot and that was it. I mean, how does this work?
Okay. Beg for time. Yeah, that is maybe an apt description of the
like
process of writing
right?
of writing a telescope.
Writing a proposal for one of these things, right?
Yeah. So there's a mode of observation that we call target of opportunity. So when you get a program approved via those telescope proposals, when you get a program approved for target of opportunity observations, what that means is that you get like a budget of time, and that is like n hours, say 10 hours or 20 hours. And if an event happens that falls in the category that you were approved for, you interrupt the observations that were scheduled and you do your program instead. So in order to do this program, we got approval for that, and we did the interrupts that way. Okay, that's a very good question.
Did you get nasty emails from the people whose observations you were interrupting?
Well, one thing that actually helps with that is that we offered people who were interrupted, we offered to include them as authors in the paper. So
I can see that would make it go down a lot more easily.
Exactly. And and also the other thing is that this telescope is not fully automated. In the meantime, I think we've gone a long way into making it more automated. So oftentimes the observers would be there at the telescope, so they would actually take the data for us and so on. So it's they would actually participate in the data taking, and that also grants.
So they deserve to be on the paper for other reasons other than just
for other reasons, exactly.
Yes, yeah.
But yeah.
Okay.
But we also try to minimize the amount of interrupts that we do. It's to respect their time. That's a very good point. Okay, so let's see the program in action in the one successful case, GW170817. It happened on August 17, 2017. The naming convention here is clear. And it was at a distance of 40 megaparsec determined via the gravitational wave signal. And it was a binary neutron star merger. Why is that important? It's because in the case of binary neutron star mergers, we have good theory for a mechanism for emission of of the EM electromagnetic signal. And that meant that at the time when this happened, it meant this was the golden event, you know, that we thought would have an optical counterpart, as opposed to binary black holes, where the possibility of electromagnetic emission is a little bit less clear that we would get anything. So here is, I like to show this list. I don't expect people to read this or anything, but just to say that there were lots of people involved in this. This was the highest profile work I have ever done, and the largest number of co-authors I've ever seen in a paper I've been in, right? I know that for people who work in the collider world, 5,000 people in a paper is every other Monday, right? But for me, this was the first time, and it was very intense to be part of this. So a number of teams had partnered with LIGO to do the observations, and then at the end, there was a big paper that involved everybody together. As I said, the BNS events, so binary neutron star events, they're special because what happens is that the neutron star material gets disrupted via tidal forces at the very last seconds or moments before the merger. And this disrupted material goes through very rapid nuclear reactions and decays that generate heat, and that heat means that the source becomes bright for a very short period of time, but it becomes bright. There are two types of emission that we observe, and all of this was theory until 2017, right? But now we know we have observed it. There are relativistic outflows, so these are particles getting accelerated, that means beamed non-thermal emission that is bright in gamma ray, X-ray, and radio. That's great, fantastic, but not relevant to us because our camera is sensitive in the optical and near infrared. So for us, the relevant emission mechanism is a subrelativistic outflows. That means thermal isotropic or nearly isotropic emission coming from this the heat of all of this material, and as it expands, it cools down, right? So that's what happens. The typical velocities that we're talking about here is 10% to about 30% of the speed of light, and the amount of mass ejected, it's only a tenth of a percent or so of a solar mass. But this, even with this small amount of material, the source is bright enough that we could see it here. For more details, there are many papers with theoretical model simulations, etc. These are two of them that you can see the results. So back in 2017, and again, I know that you have some of our LIGO collaborators there in your department, so you probably know this story better than I can tell here. But one of the spectacular things was that just 2 seconds after the gravitational wave signal came in, a gamma ray burst was detected, and that already would be sufficient to make GW170817 the most spectacular event ever, because it's clear that it's a multi-messenger event there. I would be less happy because I don't work in gamma rays, but it was spectacular already in the first 2 seconds. And then it became better as we started the hunt for the optical counterpart using telescopes all over the world. What you're seeing here is the sky map produced by the LIGO and Virgo collaborations. And here in this side is a zoom in on this most likely region. The outermost contour here is 90 percentile. And the dots that you see are galaxies that are in that volume. So this team here, they had a telescope with a very narrow field of view. So what they did was they made a list of the galaxies, they ranked the galaxies by some probability that they would be the host, and they went after the galaxies in this order. Our strategy was different. Again, each team tailors their strategy to the strengths of the instrument. Our case was different. We have a wide field of view camera, so it makes no sense to go picking each galaxy. We just scanned the entire area several times. And here what you're seeing in the photos are our collaborator, Jen Marshall. She was at the telescope at the time and took the images. And the other picture, you see two of our collaborators at Fermilab in the remote observing station that we have there, monitoring and processing the data as it came. And the sky map that you see down here is the 50% and 90% contour, and the red hexagons are the regions in the sky that correspond to the footprint of the camera. So we did cover this entire area and started looking. So at the same time that the processing of the images was happening by our pipeline, we were also looking, we call the eyeball team, we were looking at the images, the raw images as well. And the reason for that is that 40 megaparsec is really close. So we knew that if the source would be there, we would be able to see it by eye. And lo and behold, we actually were able to see it. This email was sent at 7:42 p.m. Which was just like a couple of hours after the image was taken. This was spectacular. I cannot begin to describe how awesome it was. This was one of our collaborators was able to see the image. And so now comes the question, okay, what now? What do we do, right? So the protocol here was that we were supposed to send a note via GCM. So this is the alert system. And basically you send an email out, and with that you say, we have seen a source at this location, this brightness, etc. And that basically puts a flag that claims that you have seen something. Later can be confirmed or not, but that's the way it goes. So we are there. At this point, we didn't have, today we have a semi-automated system to do this, but at the time was not at all. So I'm there typing as fast as I can. And when I turn around, I realized that, oops, somebody else saw it too and sent the email just a few minutes before us. And guess who that was? That was the team I showed earlier that had this small 1 meter telescope. It's a modest instrument with a narrow field of view. You can see their image is a little bit blurrier than ours, but it's there, the source is there. They got there a whole, I think 9 minutes before us. And this was very exciting and a lesson for all of us to learn as well, that depending on the brightness of these objects and so on, there's a role to play as well for groups that have access to modest aperture telescopes, and that is also another exciting thing. So to see more, I recommend reading this paper where there's a description of what they did, their strategy, and their results. Those two teams were not the only teams. There were 6 groups overall that independently of each other saw the source and reported it within minutes, basically. And here's a list of them for completeness. Now, if you're looking at this list, you may be asking yourself a couple of questions right now. One of them would be, first, how do you know that that source is the counterpart, right? Just because it's at a galaxy that is known to be at 40 megaparsec distance doesn't necessarily mean it is. I mean, there are other galaxies at that distance too. How do you know that's the one, right? That's one question. Another question that you may ask yourselves is 40 megaparsec is very close. There are very few events per year happening at that distance. So we really need, if we want to make more discoveries, we need to see further out, say at 100 or plus megaparsec. If this event would be that far out, would we be able to see it? Yes or no? So we answered both of these questions in our paper that describes our search and discovery of that event. I don't expect you to read all of these in detail right now, but basically what we did here was like, okay, let's pretend we didn't find it by eye. Let's see what our pipeline does. What are the candidates that we find? What is the, let's go through the analysis process, apply cuts, use, all of the infrastructure that we developed. We were waiting for this, right? And so we were working on this. And let's see what happens. Let's see if we can find this source and if it corresponds to the same, right? And the answer is yes. We have the only remaining candidate after we apply all the cuts and etc. is NGC 4993, which happens to be the name of that beautiful galaxy that hosts the event. And so this paper, although it was one of many papers that came out on the wake of that event, but I think the big strength of this paper is that I think it helped solidify the fact that we are not just finding some transient event in the sky. We actually were finding the right source. And more than that, by allowing our code to run its course, etc., it also built confidence that we would be able to do this again with sources that would be further out, because we can then simulate events, put them in, etc., and recover them. So that was very good. It was very exciting.
Marcelle, so there's a question in the chat about this automated system. The question was, is there any bias built into the, or not built in, but is there any bias in this automated process of looking for the sources?
Any biases in the process of, what type of biases you're talking about?
The question says any bias. Maybe Jim, if you wanted to ask.
I was just replying to Zohair. It was a joke.
Oh, not to this slide.
Oh,
Okay.
okay.
Sorry about that.
All right. Okay.
Sorry.
Yeah, no problem. So let's go on to cosmology, right? So as I said, that was the motivation for me, at least. Other people are motivated by other science that we can do with this. So this is the result. This came in a paper led by the LIGO collaboration of measuring H0 with that one event. A Hubble diagram with only one data point, you don't expect it to be precision cosmology, right? But it's encouraging to see that the posterior here agrees with the results that you obtain from Planck and supernova. It's about in the same overall region of the parameter space. And that is exciting and bodes well for the future. If only we can do this again and find more events, wouldn't be great, right? So we did an exercise here, which was to say, okay, let's imagine if we were able to collect, say, 8 events like GW17 or 817. This is showing more parameters in the cosmology parameter space, including W for the equation of state of dark energy. This is H0, the S8 omega M that I showed earlier. And you can see that with a modest number of events, things start to move around in this parameter space. Okay, so these are simulation. These results are based on simulations, but it shows that that it's a powerful tool if we only and motivates us to pursue this further. And here's a projection, which by now it's a little bit out, probably a little bit outdated in the numbers in the x-axis here. But doing a projection, just estimating the increase in sensitivity of the gravitational wave detectors, that would increase the number of BNS events detected. If we were able to find optical counterparts for all of them, and we just assume statistical scaling of the uncertainty on H0, it would take us not very long, to cross the threshold of 2% uncertainty, which is comparable to the uncertainty that is currently achieved by the supernova experiments. If you consider how long it took for the supernova community to go from the early measurements back in 1998 to the 2% that they got today, this is incredibly fast progress. This is the lifetime of a PhD student, right? I would be excited if I would be a PhD student and I see a time scale like this. It's not the same as what you see, for example, in other fields where progress is much slower. So I think this is very exciting and motivates us to try to do this again. Let's do GW17 or 817 again. So we pursued that, but we also decided that we wanted to have a look at the black hole events as well. The idea there is that it could be that there is an AM counterpart there, something that is not anticipated by any of the existing models or some of the exotic models that are out there. We've been searching for those events. One of the papers is one led by Zohair, doctor, who's here today in the audience. And we haven't found anything yet, but those searches have helped us a lot to develop our strategies and to learn more about the transient sky. Now, even if we don't find the optical counterparts, the idea is that we could use these black hole events to make a measurement of H0 using something that some people call dark sirens method or a statistical method. The idea there is that the galaxies, they cluster together. So galaxies in the region of interest, each of them agrees more with a different value of H0 given its redshift. And the clumps of galaxies along the line of sight would cluster together and favor specific values of H0. This is a plot based on simulations. Again, here is H0. Each curve is the posterior corresponding to one event. And the black curve here is a combination of 100 events. And the difference between the different panels is just the different uncertainties in distance and redshift. This is all simulation only for illustrative purposes. But the idea is that you would converge into the right H0 value if you had enough events. And enough means 100 plus events or so. And as you know, black hole events, they happen in an abundance that's much higher than the neutron star events. So this is not a crazy idea. In fact, we just...
Sorry,
yes.
I thought it was a question by Adrian.
Yeah, I was curious if you guys did any follow-up to the 1905-21 optical counterpart that was reported by Zwicky.
1905-21. No, so we didn't do. Let me think a little bit. I think we didn't do the follow-up of the counterpart that was detected. We did our own search, but that was for 1905-10 G. That's the, I'll talk about it later, but that one we didn't follow up, no.
Okay, thanks.
Okay, all right. So this is a sky map
Marcelle,
distribution.
sorry, Marcelle,
yes?
Another question. So the convergence you showed on the previous slide depends on actually detecting an optical counterpart to these black hole mergers, right? So
no,
it's not,
that.
Oh, okay.
No, that is, this would be without detecting the counterpart. The idea would be something like this. Here is one example of one black hole event. And the map that you see in the background here is a distribution of galaxies. You see the clumps, these are places where you have clustered galaxies. If we look in the Z direction here, you would see that there are clumps also in the Z direction. And the gravitational wave event happened at a certain distance, and the conversion of these redshifts to distance lead to a mapping between redshifts and H0. So statistically speaking, depending on where in the sky and where in redshift a galaxy is, each galaxy votes, so to say, on an H0 value with a certain probability in this posterior. And the bumps that you see here are clumps of the galaxies voting together in a certain H0 value because they are all clustered together. And basically with one event, you wouldn't know because it could be in this bump or this, right? But with many events, the other bumps, they wash out and you converge into the right value of H0.
I see.
Okay.
Thank you.
So we did this with this one event also from 2017. It was the best, very well localized, and it was in the region of the DES galaxies where we have good redshifts. So this is the result of that analysis. This was, I'm very proud of this paper also because it was a paper where we worked together between DES and the LIGO Virgo collaborations, and we put out this result where the posterior distribution is very broad. If you compare with the result that was obtained for the one that had an optical counterpart, it is ugly. But again, this was something that is expected to be powerful when you combine many events together on a single event by event basis. It is expected to be less constraining because it's statistical method, right? But it was encouraging that at least the peak was more or less in the right place, and it meant a lot that we were able to put this result out and put ourselves on track to do cosmology, not only with the ones that we find counterparts for, but also with the ones we don't. All right, but everybody must be eager to hear about what results we obtained in the observing campaign that just ended, the third observing campaign. This was spectacular from the point of view of gravitational wave detections. 50 plus events and 10 or more that had at least one neutron star in it, we think. And we pursued 3 of those events in our group. And you asked the question, why only 3? Because we wanted events that were of high significance, well localized, and so on. And we also have limited amount of telescope time, so we have to be selective about that. In addition to our team, the growth team that is led by people from the ZTF, this Wiki Transient Factory, they also had time on DECam, so we coordinated observations with them. So 1905-10G is the one that I mentioned earlier, answering to one of the questions, was a BNS merger of low significance, meaning that shortly after the first detection, it was deemed to be not of great significance, so low false alarm rate and so on. And the total area covered was only 70% of the total localization area, and only 1 night of telescope time was invested in that one. Then we had, I'll jump to this one, 1908-14BV, which is my favorite event of this season. It was an event that we think was a mix between a neutron star and a black hole, and the first of its type, of high significance and well localized. So we put on this event a lot of telescope time and covered this 23 square degrees a lot in different filters, and did a detailed analysis of this event. In addition to that, there was a BBH merger that was very well localized and of very high significance that we also covered. This one, the paper is still coming. We don't have a paper yet, but we have papers on this other 2, and I'm going to talk about them here. So question is, are these bright sirens, can we find optical counterparts for them? Well, these 2 papers summarize the results of our searches there. You know already the answer. I would be giving a very different talk if we had found counterparts for these ones. We did not. Here are the regions of interest in the sky. This is 50%, this is the 90% contour, and this is the area that we covered. This event was much worse in terms of localization area than GW 1708-17. And this other one had 2 different distinct disjoint areas here. This is the 90% contour. This one we covered all of the 90% area very well. As I said, it was the best one of this season. And these 2 papers, Garcia et al. Describes this one in detail, and Morgan et al. Describes this one in detail. Just to show briefly, because we are running short in time, what we did here, which was new with respect to the searches that we did in the previous season, other than the fact that we improved our software and response time, etc. Another thing that we did was improve our analysis. This time, we included a detailed analysis using a grid of physical parameters for the merger. Which parameters I'm talking about? These are the velocity of the ejected material up to 30% of the speed of light. And on the y-axis here, the ejected mass up to 10% of the solar mass. And the other parameter that is shown in the different panels is the opacity of, it's a parameter, actually this is the Lanthanide fraction, which translates into the opacity of the material. So varying here to more opaque and less opaque here. And the color coding here, so what we did here for the first time, and to my knowledge, I think it is the first time that this type of simulations are used in any search of this in this field. What we did here then was to simulate the signal and include in these simulations all of the observational effects. For example, weather conditions on the different nights that we observed, seeing, and etc., and all of the observational factors, so that we could extract what is our efficiency as a function of the parameter space, so that we can put limits on the astrophysical parameters. And what you're seeing here is a map of that distribution of parameters. And the good news is that, yes, we get very good coverage of the parameter space. Perhaps not in the extreme cases here, but in most of the parameter space. In particular, we highlight here in this box the two components that we corresponding to the emission of GW 170817. So if this event would have been GW 170817 and we had it looked at it, we would be able to detect it. And the fact that we didn't is something that limits, it can place here limits on the ejected mass or the velocity or the lanthanide fraction. So this is, I think, very interesting and also helps us determine, and this is something that is coming in a follow-up paper now, is with these tools, with these simulations, we can now improve our strategy so that we can reach the corners of parameter space and really claim that we're doing the most efficient possible searches for the EM counterparts of these events. Now here, we have the same map, so the same code applied to the 0814 BV event. This is the an SBH merger. And here you notice, if I blink between the two, that it's much worse coverage than in the other case. And the reason for that is that this event is much further away and the flux goes down with distance squared. So, it gets very hard. But it's also an exciting result. I can talk about more about it. And tying it back to cosmology, this paper here, which we also put out this year, shows a combination. After we did GW 170817 and the 0814 events separately, we said, okay, now let's combine them. And more than that, let's combine with the event of this season, which is the 190814, this event, using it as a dark siren. We didn't find a counterpart, but let's use it in the same way as we did with the 2017 event. And what we see now in red is the result of combining all of these events. And I'm very excited that we are making progress towards not only observationally, but also in the analysis side, producing H0 measurements that are slowly but surely converging to the level of precision that we need for cosmology. So to close here, what I presented today and am very excited to talk about is the results of our program, the DESGW program. We are, I believe, leading the charge of search and discovery of EM counterparts of gravitational wave events. We had 3 spectacularly successful observing campaigns. In particular, in the second observing campaign, we participated in the discovery of GW 170817, which was fantastic. And we are also pursuing black hole events, either in both ways, trying to identify optical counterparts if they exist, and if not, using them for cosmology, using this method that I just described of the dark sirens. We published a first measurement together with the LIGO collaboration of using a black hole merger, and results of the third observing campaign that we just finished this year includes improved searches and cosmology results combining bright sirens and dark sirens. I'm very excited about this. Thank you very much for inviting me to speak, and I'll take questions in the remainder of the time.
Great. Yeah, thank you very much, Marcelle. If people want to unmute and clap, we can also have actual applause.
Oh, thank you.
So if you have any questions for Marcelle, maybe we can use the the raise hand feature, and I'll go in order. So the first question I see is from Zohar. So go ahead, Zohar.
Hey, Marcelle. That was a really nice talk. Thank you. I was wondering, what is like your dream source to see, like a neutron star black hole or a binary black hole or a double neutron star? Or what do you think we would learn the most from, and what would make you most excited?
That's an interesting question. And I'm realizing as you speak, I'm realizing that I don't really have a favorite. I want to see many of them. I want to really like see this plot. Where is it? Yeah, I want to see this plot here get so narrow that we can actually go in here and see, you know, if we are agreeing more with the supernova or with the cosmic microwave background folks. So I don't really care. Just keep them coming.
Thanks.
So sorry, I don't know. I didn't quite understand the protocol for these questions, so I'm just going to shout out. Can you see the light from some mergers, say binary neutron star mergers, that are actually so far away that they could not be detected by the gravitational wave telescopes?
Oh yeah, Actually, I see what you mean. If we could have seen, for example, these events without the gravitational waves, right? I mean,
right. I mean, in particular, what I'm thinking is if your range of view, if the distance at which you can see such an event is greater than the distance at which the gravitational wave telescopes can see it, then you can see more events. Now, of course, you don't have as much, you don't have the benefit of the information that the gravitational waves are giving you, and particularly you don't have the gravitational waves telling you where to look, which I suppose may scupper the whole idea. But
that's
I
the
wonder
problem.
if maybe with a slightly different, maybe with a different approach, if you had something that had an even wider field of view and you scanned the whole sky, could you potentially see some events? You wouldn't now have the gravitational waves to tell you that it was a binary black hole, binary neutron star merger, but maybe just from the optical spectrum and its time dependence, you could tell that it was a binary neutron star merger. I just wonder if you think there are any possibilities in that direction.
Yes, that's a very good question. So in this paper here, one of the things that we asked was like, okay, could we see this? So how far out could we see this source, right? Because for this one, we have the flux and we have the distance. So it's easy to just put it further out and say, okay, how far out can I see this source? And for a source of this absolute brightness here, oh, sorry, I clicked it away. We could see this at a distance that is several times greater than what LIGO can see. You know, so LIGO can see them out to maybe 200 megaparsec, and we would be able to see maybe 3 times further with these images, without actually going deeper. And if we needed, we could put more telescope time in it and co-add the images, etc., go to, you know, lower signal, higher signal noise, and capture it. The problem is that because these events are short-lived, to do that without knowing where to look, the probability is very low. And there's a paper, actually, Zohar is in the room. He did a paper where he did a search that we called an untriggered, you know, search, which was using existing data sets from DES, looking to see if there would be a kilonova that is how we call these optical counterparts present there. And we didn't find any, and we didn't find it that with the data that we had available, we were not very sensitive to it, you know. In order to do that, you probably would need something that would be a dedicated survey that is wide area and deep, like going very deep in flux, to be able to do this. And this would be difficult. I would say that even for LSST, this might be difficult, you know, because of that. But that's a very good question. Thank you.
John, so Zohar has put in the chat the preprint to this paper that Marcelle just mentioned. 1611-08-052. So I have maybe one last question for Marcelle. So you showed this picture of the simulations of observing black hole mergers and how you could slowly start to narrow in on the value of H0. So given the rate of the current observations, how long do you anticipate it to take before we can actually start to differentiate between the supernova and the CMB, like to start to pick one camp for H0?
Oh, okay. How long? Okay. So, well, that will depend on how often we'll be able to do a search like this one, right? So my dream is to be able to do a search where you see mostly yellow throughout this entire panel here, right? For many events. If you were able to do that in the coming year or so, it will depend a lot. So for example, in this case here, we did a decent job, right? It was not bad. But the problem with this event is that, well, first, it's of low significance. So it could be that it's not even a real astrophysical event, right? Also, the localization area is so large that we were able to cover only 70% of the localization area. So what I'm hoping for is that in the next observing campaign, that with improvements in both LIGO and Virgo, we are going to get more events that are binary neutron star events like this one, but with localization areas that are small, like this one, small enough that we can cover them well, cover 90% of the area, and so and do it. If we are able to do that for, say, a dozen events, we will already be, and this is my yellow, my ugly yellow plot here. You know, so with 10 or so events, this is just the square root of the errors and of the uncertainties I'm doing here. We would already be in the ballpark of a few percent uncertainty. And if we can go to tens of events, then we would cross this threshold soon. So again, this evolution here is assuming an evolution in sensitivity that is reported by the LIGO collaboration in one of their publicly available papers. If they continue, and they have a very good track record of keeping up their promises, if they continue to evolve along this trajectory here, then provided that we have an efficient program to detect the counterparts, it could be not very long. It could be less than a decade, 5 years or so before we are at the place where we have something to say.
Okay. Yeah, thanks. I missed the slide, so thanks for showing it again. Any other questions for Marcelle? So just as a reminder, she is quote unquote visiting tomorrow as well. There was a Google Doc that was sent around, so I think there's still a couple of slots available. So if you wanted to chat with her, either ping me, you can email me, or go to the Google Doc and sign up for a slot. But if there's no more other questions, let's thank Marcelle again for this really nice talk. Very interesting subject.
Thank you. Bye-bye.
All right, see you tomorrow.